Hey, hi everyone. Welcome to the Topos Institute Colloquium. Today we're pleased and honored to have Fabio Gadducci from the University of Pisa, who'll be speaking to us about gs-monoidal and Cartesian categories. So Fabio, whenever you're ready.
So hey, I'm ready. I'm fine. Thanks for inviting me. And the idea of the talk is actually kind of a survey of some recent results that we have done with myself, Davide Trotta, together with Andrea Corradini and Tobias Fritz, and to try to, how can I say, to give some idea about the taxonomy which exists between some kind of enriched monoidal categories like gs-monoidal ones to up to Cartesian categories, and what we can say from the point of view of the structure of the free categories which are built out of a signature. I'll try to give some details and to, how can I say, to be kind of didactic in one step after the other. So, first of all, some historical remarks. I'm a kind of history buff, so I'm always happy whenever I have the chance to discuss about the history of the topic. And well, after the work by Louvier on functorial semantics, there have been a lot of research on from the community of the algebraists and formal method people that started looking for some categorical presentation of partial function, relation, flowcharts, automata, and so on and so forth. Because, I mean, Louvier was pointed out the connection between terms out of a signature and Cartesian categories, but of course, I mean, if you consider, for example, computer scientist, it was be interesting also to be able to discuss about partial function or relation, or in general flowchart schemes, which are an abstraction of classical programs. And well, there have been a lot of works. Most of them have been forgotten, rediscovered along the years. But from mid-60s, the work of Ox, for example, in X categories, S monoidal categories by Fender, DH symmetric monoidal categories by Henke and his group in 77, flowchart theories and so on. Part of this stuff is surveyed in the paper by Seilinger of some years ago. But let's say there have been a lot which have been kind of forgotten. It's a bit surprising given the amount of details of interest that you can find there about precisely the connection between visual formalism and algebraic presentation. And it's also funny, for example, that Hotz in 65 never mentioned Louviers in the bibliography, while instead clearly there has been some inspiration coming from there. Okay, it's true that it was a peculiar former East German journal and in German, by the way. So let's say it was, how can I say, there is a long story, so to say, which takes then up to the string diagrams, which are nowadays the preferred way to present, how can I say, algebraic formalism. Again, it was a kind of swap of perspective, because initially we were good at drawing visual formalism. We wanted to have some algebraic presentation in order to manipulate them, and vice versa. Now we know that once we are able to get a visual formalism, we have now tools which allow us to enable manipulation in a much easier and more intuitive way. There has been some intersection with linear logic. In particular, I will mention implicitly some of the results by Bart Jacobs with his work on the semantics of weakening and contraction. And let's say all this work, like I said, received a new impulse from the wide adoption of string diagrams nowadays. First of all, for quantum calculi, but in general, as a nice intuitive formalism for system specification. Okay. My personal journey, I started working on somehow on these topics on my PhD thesis. Of course, I mean, let's say it is some time ago, and then it was not always easy to find literature like it was now. So actually, there were some false starts from the denomination point of view, in the sense that I reuse some name that was already adopted in the past. So I mean, at a certain point, we we agreed with Andrea Corradini about using gs-monoidal, which stands for garbage sharing monoidal categories. That to say, monoidal categories which have suitable arrows for representing garbage and share. I mean, if you think, not so different from what could be CD, that to say copy discard. The intuition is exactly the same, but at the time it was quite fancy GSM cell phone, and so we thought we were very clever in using this this acronym. In the past, we used that for again. We were still working on the older perspective, that to say we wanted to be able to give an algebraic presentation of visual formalism like graph and graph rewriting. We used that in the end for giving functorial semantic to partial and multi-algebra. And recently we have been using that a bit for string diagram rewriting, and very, very recently about Markov categories, and in particular weakly Markov categories. I don't know if I will have the time to hint at that, but I mean, let's say that there are a few references that you can find at the end of the talk. Very well, this is the plan of the talk. gs-monoidal categories and their relation with Cartesian ones, which is nowadays is kind of folklore. The classical paper is by Fox in '74, but I mean, there have been, like I said, a lot of work before that, and so let's say I consider that as a kind of folklore result. Then I will introduce some specific new classes, which is Oplax Cartesian category, that to say monoidal categories with a pre-order on the homesets, and I'll show why that one can be of interest, and which is, I think, almost new in the sense that these results are more or less scattered in the literature, and I'll try to give a uniform view of those. And then I'll try to give a structural analysis of the free categories out of an algebraic signature, which is also kind of almost new. Again, there have been some previous results a bit scattered in the literature. Then completeness for the functorial semantics of this kind of Oplax Cartesian categories, which is a result which is presented in this applied categorical structure paper of last year. And then again, I'll try to, if I have the time, to present a bit the graphical notation for gs-monoidal category, gs-monoidal, Markov, restriction, and so on and so forth. Okay. And first, let's go. What is a strict gs-monoidal category? It's just a symmetric strict monoidal category with two families of arrows, share and L. Okay. I decided to make a compromise between GS and CD, but the intuition is always the same. Because this one basically tells me that whenever I have an object X, I have an arrows which provide me with two copies of X. And L is just something which tells me that whenever I have an X, then I can throw it away, discard it, delete it. And it goes directly to the identity of the monoid, of the tensor. Okay. They are subject to some axiom which make each object a comonoid in C. More precisely, these are the axiom, which basically tells me the first one is basically telling me that we are commutative. The second one is that the del is actually gives me the identity of the comonoid, and then I have associativity. Okay. The bottom line is that if I have this axiom, there is a canonical arrow for each object. There is a canonical arrow from X to N, where it's just basically N copies of X. Okay. But then you can also add some axiom like this one, multiplicative one, which basically tells you how the copy and discard, share and delete interact with the tensor product. And well, these are the two which are still rather intuitive, I would say. And the key result is that if you add this axiom, the canonical arrow is actually the unique one. Okay, the canonical arrow is actually unique. So, very well. Now we can give in terms of the interaction of an arrow with these two, with the share and the deletion, some additional terminology. So an arrow if functional is whenever I apply the arrow and then I do the sharing, then it's like having two copies of it. That's to say, first share the input, if you allow me, and then to put two copy of f. And it is total if whenever I have an arrow of f and then I apply the delete, then I basically throw away the f. Okay. We will see this is not, these denominations are not by chance, but the first thing that I want to point out is that this one. If in a gs-monoidal category all its arrows are both functional and total, then C is a Cartesian. Okay, with a chosen Cartesian product. So Cartesian monoidal. Okay, very well. And then we can say a bit more. What happens if only one of those two axioms are actually true? They actually hold in the category. Well, by the way, this is why it is Cartesian monoidal, how you can get the unique arrow which is linked to a pair FG, then you share, then you do the duplication of F and G, and then you apply the two deletion. Okay? Easy calculation to show that it is actually the unique one. Okay, very well. But I prefer to point out this taxonomy, which is again in the literature, but I don't know if it has been so clearly pointed out. That's to say, symmetric monoidal, gs-monoidal, and Cartesian. The one I already told you. Well, the point is that it is a Markov category if all the arrows are total. And it is a restriction categories with restriction product if all the arrows are actually functional. Okay, I'll try to give more intuition why this occurs, but this is, how can I say, the key taxonomy. Okay, restriction with restriction product, because the restriction category in general are more general, since they do not actually require the existence of an underlying tensor. Okay, but in general, I can say that we have this taxonomy here. Okay, and all these you will find has been discussed in this paper with Tobias Fritz and others. Very well, let's try to give additional hints about restriction categories. As you know, the key idea of restriction category is that whenever I have an arrow of F, I have another arrow which is called DOM-F, which represent, how can I say, the total restriction of the original arrow. Well, in gs-monoidal categories, also this is well known, you can represent it like this. Okay, you duplicate, then you put in parallel the identity with the F, and then you discard the F. This one has the effect of basically throwing away all those inputs which are not valid, where F is not defined. So this one basically is allow just the passing of all the value which are for whom F is defined. And another key issue which always hold for restriction category is that if I apply, if I calculate F and then apply DOM-F and then apply F, this is just the same as applying directly F. And this one is true. Why? Because the duplicator, because all the arrows are functional. So this one is like writing one copy of F and then to apply the sharing. And so, like this. Very well. If an arrow is total, then its domain is just the identity. Very well. Okay. Well, there are plenty actually of categories where we have some kind of gs-monoidal product. Some of them, actually, in general, it is a non-strict product, okay? But it's quite standard to give the axiom for the strict version and assume that the models are actually non-strict, okay? And some of the categories are set, of course, which is Cartesian monoidal. Category of set a binary relation, which is actually properly GS. Preorder, the category of preorder and monotone map. This is Cartesian monoidal and will play a key role in the functorial completeness that I'll show later on. Okay. The category of set is strict partial function, that to say which maps bottom to bottom, and it is a restriction category. And the category of set of stochastic maps, which is actually Markov. Okay. Very well. Now we can give we can move a step further and to consider to have a preorder on these categories. Okay. Not plus Cartesian category is just a gs-monoidal category, which is preorder enriched and such that, well, these two inequalities hold. These basically say that you can consider then if you see that in relation like the usual partial order which holds for relation, because this one, the arrow here in relation from x to the unit of the tensor actually maps every set to the singleton. Okay. While instead f can be in principle a partial function, so we'll map only some of the element of a set x to the singleton. So it's clearly less defined than the other. Okay. And the same for this. I mean, this is just to give the intuition, but for the time being, it's basically just a syntactic game. Okay. Preorder enriched with these two additional conditions. Okay. What is interesting is that if I choose the tensor product and I choose the order, then there is only one possible structure for share and L. Okay, there is only one possible arrows doing the sharing, and there is only one possible arrow doing the deletion. Let me show. And in fact, basically this one, dom f is smaller than the identity, which is true in general, right? Because f is partial, so it's not necessarily valid. It doesn't necessarily map all the elements of A to another element in B. And we have that the domain axiom holds, but only up to preorder. Of course, should we have moved to poset, these two would coincide. Okay. Why we choose preorder? Well, because we started applying this idea some time ago in order to model rewriting. So we have this very, very high recipe, which is also considered folklore. Choose a suitable category, trees, graphs, whatever you like. Whenever you have a rule moving from term S to term T, then you add an inequality like this, S less or equal than D, and then you generate the free Oplax categories. And the preorder give you the rewriting relation between the elements. You can also do, of course, poset, but then you would collapse all the elements in the equivalence in the equivalence relation given by reachability, and this one is not always a good idea. Okay, and you can even move further. I won't talk about that, but instead of having a preorder, you could have also a two category, and then actually you are also able, thanks to the whiskering or the interchange law of two category, to talk about concurrent rewrites. I won't discuss at all about this, just to give the idea. Very well. So let's say this one, everything so far, everything has been given, how can I say, in a quite straightforward way. Okay, category, additional arrows, some law holding for some of the arrows. Let's try to be a bit more, how can I say, general and abstract. Okay, what is a lax symmetric monoidal functor? Well, it's just a functor between symmetric monoidal categories, which is subject, which has two natural transformations, like this. Okay, it is subject to some coherence axiom. Okay, It basically tells me that f of A times B is not the same as FA times FB. There has to be some natural transformation, but they are not the same. Okay. And if it is a lax symmetric monodal functor, if additionally it preserves the symmetry. Okay. Very well. It's closed under composition. And as you can imagine, Oplax, bilax, and so on are defined as expected. Oplax simply means that the natural transformation goes the other way around. Okay. And bilax, that it is both lax and Oplax, and there is some additional axiom holding. Okay. But I'll focus most of my attention directly on lax symmetric monoidal functors. Very well. What is a monoidal natural transformation? Note that I put natural on parentheses. A monoidal natural transformation is just a transformation within these two triples such that, okay, it tells me that they have some commutativity with respect to the structural arrows. Okay, very well. If they are symmetric monoidal, they satisfy the same axiom. What is naturality? Basically tells you that the naturality square has to commute. But the definition of transformation is more general. It's just a set of arrows satisfying some properties, not necessarily naturality. Why is this interesting? Well, because in principle, share and L can be consistently given as monoidal transformation. Instead of giving all the axiom, blah, 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 and so on, well, these are two monoidal transformation between these two symmetric monoidal functors. Okay? And we will use these later on. Okay? If they are natural transformation, then it means that all the arrows are total and functional. That's to say, we get Cartesian monoidal. Okay? So, being or not Cartesian actually depends just on naturality of this transformation. Okay? And if, for example, del is natural, then you get Markov category. If share is natural, then you get restriction categories. Then we can go on and then define also a taxonomy of lax monoidal functor. And if a functor satisfies the triangle on the left, we call it lax affine. And satisfy the triangle on the left concerning the share, we call it lax relevant. Why? Well, because this terminology was introduced in a slightly different context, in less general than this, by Bart Jacobs in the Semantics of Weakening and Contraction paper. Okay? Very well. Then at this point, we can what is a lax gs-monoidal functor? If it is both affine and relevant. Okay? So we have the usual functor, but then we can require, if we have a gs-monoidal category or Markov or restriction, we can ask some additional property for this. Okay? Closed under composition, Oplax, bilax, and so on and so forth. Very well. Now, commutative monads. Okay, and then I'll show why they are relevant for us and for the presentation that I'm giving concerning GSM. Now, commutative monads are usually presented through the notion of strength and some additional properties, but there is a nicer presentation of commutative monad. A monad like this on a symmetric monadal category is commutative if T is actually a last symmetric monadal functors and eta and mu are monoidal natural transformation. Okay, the two definitions are completely equivalent, and this is folklore. Okay, but I mean, it's more convenient for me to present it like this. Okay, basically, it means that they, beside naturality and so on, they satisfy this property, that's to say, the unit of the unit of the tensor is like the arrow of the structural arrow of the lax symmetric monoidal functor, and plus a couple of axioms like this. Okay, I'm making them explicit, but I mean, the first bit is already enough. Okay, very well. And then, how can I move behind commutative monads? Well, affine monad is if they preserve the deletion, relevant monad if they preserve the share. Okay, so now we have also a taxonomy of, we have lax monoidal functor and various extension. And then we also monad depending on the property of the underlying functor. If it is a symmetric monoidal or lax monoidal or lax relevant. And of course, a GS monad if it is affine and relevant. That's to say, basically, T is a lax GS monoidal functor. Okay, so far? Okay, here we are still just playing with terminology, but there is something interesting now. What about Kleisli categories? Well, you know that if you, the Kleisli category of a commutative monad on a Cartesian monoidal category C is symmetric monoidal. Okay, this is also folklore. What we point out in the paper, and it's kind of known but not necessarily well understood, is this. Actually, it is gs-monoidal, with the notion of the deletion arrow and the share arrow completely determined like this. I mean, apply the del in the underlying categories and then the unit, and the same for the share. So you basically end up with a gs-monoidal category. Not only that, you can play a bit more depending on the property of the underlying functor. That's to say, if it is an affine monad, relevant monad, and so on. Okay? Okay, so monoidal product and GS structure are canonically induced. Okay, like this. And, well, so now this is the taxonomy that I was showing before. gs-monoidal, Markov, restriction, and Cartesian. What happens if I have a commutative monad? Well, all the Kleisli are gs-monoidal. Okay, very well. What happened? Still the same taxonomy, but now I have an affine monad. Well, it works like this. If I start with a Cartesian monoidal or a Markov category, I always end up in a Markov category. If I start with a restriction category of a GS monoidal category, I end up in a monoidal category. Okay? But then you may ask, well, it's quite different from the usual definition of affine monad that I heard so far. Not really. Let me try to point out how come. So, this is the requirement for the affine monad that I gave. Okay? Clearly, if the diagram on the right commute, also the one on the left commute, for all x, of course. Okay? The fact is that if we are in a Cartesian or Markov category, also the reverse is true. Because this triangle here always hold in Markov categories. Because the identity is terminal. Okay? So, everything in the affine monad, if we start with a Markov category, the requirement boils down to the identity is isomorphic to the identity with after the application of the functor. So it actually coincides with the usual definition of affine monad. But it is more general because if you are in a restriction category, you don't have terminal objects. Okay? So you cannot say that an affine monad preserves terminal object. You don't have a terminal object. But instead, this definition is still applied, can still be applied to restriction and gs-monoidal. Okay? What happens if I have a relevant monad? Well, I think you understood the pattern now. Okay? Whenever I am a Cartesian or restriction, I always end up in a restriction if I have a relevant monad and Markov and gs-monoidal. Okay? And I have a gs-monoidal monad. If I have both, well, everybody stays in its own group. That's to say, if I consider a gs-monoidal monad in a Cartesian category, then the Kleisli is Cartesian. In fact, it would be nice to call this kind of monad Cartesian monad, but unfortunately, the term is already booked, so it is with a different notion. Okay, so very well. So this is as far as the taxonomy for categories. What happens if we have instead Oplax? That to say, we have the pre-order on top of each category. Well, work exactly the same. What is a Oplax Cartesian functor? Well, now the triangle are not equality anymore, but inequalities, like this. Okay, since I have a pre-order, I can easily discuss about this. Okay, very well. Then I can play exactly the same trick as before. This is an affine monad Oplax. It preserves somehow the deletion arrow, and this one is relevant. It preserves somehow the share arrows. Okay, very well. Everything lives exactly as before. And if you want about the pre-order, well, what happened the pre-order for the affine, for the Oplax affine monad? Well, it still can be simplified because this triangle here always now for all possible Oplax. So for Oplax Cartesian categories, we have a somehow simpler notion. But again, it doesn't matter. It is completely equivalent to this one, which is how can I say, more standard, more symmetric, so to say. Very well. And now we end up exactly with the same taxonomy that we have before. Now, instead of having just gs-monoidal, we have Oplax Cartesian. Instead of having Cartesian monoidal, we have pre-order-enriched Cartesian monoidal, and so on and so forth. Well, it works exactly as before. For example, if I have this taxonomy and I have a Kleisli category of the Oplax affine monad, it works exactly like this. Okay, that's to say, whenever I take the Kleisli of the Oplax affine monad over pre-order-enriched Markov, I end up in a pre-order-enriched Markov, always. Okay, very well. So if you want, this is a nice machine, if you want, in order to obtain Markov restriction and Oplax Cartesian. I mean, you take the monad that you like, you check which are the axioms that holds, and then you know how you can get one of those category. Can I say tellurate over the monad? Very well. Now, the main result of that paper is actually this Oplax completeness. We worked a bit in order to try to show that gs-monoidal categories are precisely there is a sound completeness result for functor towards relation. It doesn't work. Okay, but we have something like this. Pre-order is the Oplax Cartesian category whose objects are preorders and whose arrows are monotone maps, okay, with the obvious order on the monotone map. Well, given an Oplax category C and two arrows S and T, then S is less or equal than D if and only if the image of S is less or equal than image of T for all possible Oplax bicartesian functor from C to preorder. Okay, so now basically it says that in order to check inequality, you may simply check what happened in preorder, which is clearly in general much simpler than just playing the game with the arrows of C. Okay, and what happened with rel? Well, we are almost there in the sense that there is an obvious functor from preorder to rel, which is Oplax bicartesian, but unfortunately, it doesn't map identities to identities. But it is lax on identity. It doesn't really map an identity to an identity itself. This is the order. It basically assume that whenever I have a pairing, I took the, how can I say, the downward closure of the image of X. Okay, and this one gives me a relation. And then we are almost there with rel, but not really. And so we are not very, very, very happy, even if we are still thinking how we could find some way to have a proper functor tower rel in order to guarantee completeness for our stretch. Okay, so okay, now I want to move to something a bit more specific for whom computer scientists are usually more happy. Like I said, usually we start, most of the things actually start between algebraists or computer scientists in order to have a way to describe partial function, partial algebra, multi-algebra, flowchart, and so on and so forth. So the idea is that I have somehow a many-sorted signature sigma, and of course, whenever I have a signature, I can decide to build the free cut, the free category, the free Markov category, the free Cartesian category, and so on and so forth. Okay? Basically, in a completely inductive way. Then, the idea is that, well, which is the structure of the arrows of this free category? Okay? Why that? Well, we will see that to be able to give a structural decomposition of the arrows actually suggests something about which models are meaningful for each of these categories. Okay, so M sigma is basically the free monoidal category built out of sigma, a signature, a generic multi-sorted signature. Or if you want something goes where every operator goes from n to 1, if you have just one sort. Okay, well, then if I consider the free category, each arrow from n input and m output can be decomposed like this. Okay, of course, there are many possible, how can I say, concrete arrows, but at least there is one with this shape which I can consider the canonical decomposition. Okay, what happened with the, and of course this one works, why? Because we are starting with a signature where the target is always 1. Okay, every basic operator, every generator goes from n to 1. Okay, and then now what happened with the symmetric monoidal category? Well, basically at the beginning I have some permutation. You can consider 1 to n basically the variables. I have some permutation on the variables, on the input, how you may like that, and then later on I have an arrow which can be then further decomposed like this. Okay, in general it's not true if I have an hypersignature, but for a signature it works. Okay, well, if I have a Cartesian monoidal, how it works? Well, everything is, I throw away some input, I do the most sharing that I want of the various inputs, and then I have an arrow which is purely symmetric monoidal. That is to say, some permutation and then some arrows. Okay? Very well. What happened with restriction? Well, the decomposition is of this kind. I have some sharing at the beginning, then I have some symmetry, some symmetric monoidal arrow here, that's to say an arrow from the free symmetric monoidal category, and then I have some deletion here. Okay, some application of the deletion. What happens if I have only one? Well, let me, so if I'm in a restriction category built freely out of a signature, each arrow which has target 1 can be represented as a pair like this, S and D, where S is a term, okay, out of the signature, and D is just a subterm closed set of terms, which is called its domain restriction. It's basically telling you to throw away some of the possible values for whom S could be defined. Then, the funny thing is that in the partial algebra literature, this kind of arrows are called conditional terms. And a conditional clean equation has this shape. S is equal to T for all the objects which are in the domain of these subterms. And the definition is given by Berner. I mean, this is one of the classical references. So what happened? Now we have an easy way to give like in the style of a functorial semantics for total algebra, the same one for partial algebras. I simply give a signature and a set of conditional equation, and then I take the lax symmetric monoidal functor from the restriction category built out of sigma to par. And this one characterizes the conditional varieties of partial algebras. This is a, I mean, this is a known result, even if it has been reformulated in a more modern terminology. Okay, very well. How are what is the shape of the arrows of a Markov? They are a bit more difficult. Okay, they are something like this. Basically, you throw away some of the variable, and then, I mean, you keep on sharing. Well, let me give this the compact way. Okay, so I throw away the variables. Okay, then I have some share like this, and then asymmetry. So basically, throw away the variables, and then you can share all the intermediate types. Okay, and for GSM, it's more difficult because you cannot throw away anything. Okay, so you have terms of this shape. But this one suggests the form of the a correspondence with a graphical interpretation for these arrows. Okay? Why? Because a signature can be considered as a graph. Okay? Then typed graphs are commas in the category of graph with respect to the signature. And then I can define term graphs, trees, and so on, just plain on the fan-in and fan-out of a node. The fan-in is the number of incoming tentacles, and the fan-out is the number of outgoing tentacles. I'll show in a moment, okay? So consider this signature. Very silly, we have three sorts, bullet, circle, and diamond, and three operator, F, G, and H. Okay? Is everything fine? Because, of course, this one is quite computer scientist-oriented as an approach. Okay? Well, what is then, for example, a graph where the operators and the nodes are taken from this type? Well, something like this, for example. Okay? So we have 1, 2, 3, 4, 5, 6, 7, 8 nodes, still 3 operators. Bear with me, I try to be as simple as possible. Okay? 3 operators, and, well, some sharing and some duplication and so on and so forth. Now, all these are leaves because they have no fan-in. There is no incoming tentacle. Okay? There is no tentacle going into the node. Okay, so if you want, they are not in the target of any operator. And these two are proper roots. That's to say, the fan-out is 0. They are not in the source of any operator, so to say. And they are not leaves. Okay? Well, now let's try to give some correspondence. If I take the free gs-monoidal category of the signature, any arrow from an n tuple to an m tool is actually a term graph with n ordered leaves and m ordered nodes, the latter possibly with repetition. For example, this one is a term graph which has source, circle, bullet, bullet, diamond, diamond, and target, diamond, circle, diamond, diamond. And here you see input 1, input 2, input 3, input 4, input 5. I mean, we are talking about spans in the end. Actually, co-spans, okay? And I have some this internal node which is used and duplicated, and I end up here, okay? And this one is actually an input, and it's a leaf, but also a root, also an outcome, okay? Very well. What happened then with Markov? More or less the same, but it has to include all the proper roots. Okay, so I add an axiom. I put a restriction on the normal, on the canonical form. Okay, so which are the proper roots here? O1 and O4. But you can argue, But is not this one also a term graph? And then if you want a term in the category, yes, but it's not in normal form. The normal form associated to this graph is actually this. It's Markov, right? So basically, since it's not in the output, it means that I applied the del in this node. And so I'm throwing it away. Because the del is a natural transformation. Well, now I can choose instead to go to the restriction. And is exactly the same, but then now I have to include only proper roots and leaves. Okay? Proper roots without repetitions. Okay? Well, I'm not putting the last one, but the idea is that, well, if you are both Markov and restriction, well, basically you end up with n leaves and m trees. That to say, you end up exactly in the usual tree representation of a Cartesian category out of a signature. Okay? Very well. Now to the future work, and I think that I'm right on time. So hey, right? So more completeness result. Of course, the result that I've shown for pre-orders also for partial orders. And it still goes then to the, but I mean, again, we would really like to go to relations or some restricted relation. Can we get some completeness for I mean, for restriction, we know the completeness for restriction is mapping to the category of set a partial function. What about Markov? Would be interesting to see. More, I mean, since we know that now we can play with some structural axiom for a Markov, we would like to do the same also for conditional marginals, which are key issue in the Markov and in general the categorical stochastic semantics. And of course, we would like also to have a bit more structure, for example, traced Oplax Cartesian categories. And the fact is that paradoxically, the graphical presentation is already there because there's basically cyclic term graphs. Okay. The point is that would be nice to be able to lift all the taxonomy that you have seen so far also to the traced case, which is not happened so far. Okay, and that's it. Thanks for listening. This is a small.
Thank you so much. Thank you so much, Fabio. Thank you.
Thanks to all the people listening.
Thank you. Okay, now we have time for questions. So this is how we do questions on the Topos Colloquium. If you're in the Zoom chat, you can raise your hand, and then I'll call on you. You can unmute yourself and ask your question. Or if you're not able to unmute yourself, please feel free to type in your question in the meeting chat, and I will ask on your behalf. Okay, there's any questions from?
Yes. Hi. Hello, Fabio. It's Valeria again. I think one of the things that I wanted to ask you, which is presumably future work, is as you're saying, the trace operator. You don't know how to do with it quite yet. I think very much, right? So I mean, the previous versions are about logic, about contraction and weakening. Do you think there is anything more logical about trace that we can say?
Well, the idea of using traces was basically a way to represent compactly feedback, right? And if you are Markov with trace, actually you have something which is really, really similar to a recursive operator. So I'm quite confident that it is possible. You know that you have, I mean, the way that Cartesian categories with trace interact is quite peculiar, right? Because you get immediately a lot of additional operator like the new and others. And I mean, you can use, for example, Markov, GS, and restriction, playing exactly the same tricks. I mean, the traced there works, it's fine, but I'm not so sure if it is still possible to play the usual, the taxonomy tricks that I've shown so far. Which is, beside that, I agree that logically you can find a lot there already, but I mean, I'm more moved so far by the way of lifting all these nice taxonomy to traced Cartesian, if you want.
Right, but you do have a problem there, right? Because fixed points kind of don't behave very well with logical things, like, you know, the famous result about, I mean, fixed points make everything inhabited, which means the logic is inconsistent.
I agree, but if you are a traced Cartesian, it's slightly different to have actually how can I say, recursive Cartesian. Let me put it this way. And you can define traced gs-monoidal on traced Markov, and you still have something which makes completely sense without any peculiar problem about inhabitants, and which are actually typical of traced Cartesian category. I agree. The fact is that you have to weaken the structure and in order to still get something which is logically meaningful.
Makes sense, yeah. Thank you. That sounds good. And bye-bye.
Thank you, Valeria. Thank you, Fabio. I see that we have a question in the Topos room.
Yeah, thanks, Fabio. I was just not sure whether I followed correctly or not, that you were talking for a while about this taxonomy of different kinds of commutative monads and how they relate to the taxonomy of gs-monoidal categories, and upgrading that to the Oplax case, which is all very nice. And then you talking about presentations of free various kinds of gs-monoidal categories. Are those totally orthogonal projects so far? You mentioned the graphical presentation at the bottom of this slide for the Oplax case, but you were just talking about plain free, like Markov categories, right? Not with the local pre-orders, or?
Oh, well, actually, from my point of view, the pre-order is basically a way of modeling graph rewriting.
Right.
Whenever I have an arrow whenever I have an inequality from S to T in the offset, it basically means that I can move from the arrow of S to the arrow of T, doing some rewriting step. In fact, just have a look at the let me see if I can. Sorry about that. I don't remember where it is. Here it is. If you look at this, this is basically telling you that consider the duplication of f, x, then sharing, and 2f. If you look at that as a graph, there is an obvious morphism from this to the other, okay, which basically collapse the two instances of f. And the same for the other. And then the trick is, whenever you have a rule moving from S to T, then add it as a basic inequality. Then put in the mix these two, and then you are able to give an interpretation of all the possible of all the possible inequality in the OM set in terms of rewriting.
Sure. So you could think of these free structures. You're constructing this first, giving a pre-ordered thing with inequalities based on rewriting, and then, well, maybe you actually quotient if you want to.
And if you want to, you can quotient, exactly. Exactly. But again, sometimes you want to take two, how can I say, two graph distinct, even if they are they can be reached one from the other, because they represent different instances of data resources and so on and so forth. But it would work exactly the same with partial order instead of pre-orders.
Sure. Yeah. Thank you.
You're welcome.
Thank you. I see that we have a question from Maria. Maria,
Yes,
maybe you
thank
can
you very
unmute.
much, Fabio. I would
Oh,
like to ask you, hello, hello. I would like to ask one question and another one with, and so would like to ask you about regarding the free structure, the gs-monoidal category you built. What requirements do you ask to the free structure so that it can be applied in computer science? So that what kind of computability properties do you ask? This
oh
is
no,
in
no, I
general.
mean, it's free in the usual low-level computer science approach. That to say, I have some generator and then I inductively build all the terms. Okay?
Yeah, but do
Like,
you require some decidability properties or no?
no, not necessarily, no. I mean, it's
No.
like I'm building programs.
Yes,
I
but
have
do
a
you
set-
need a normalization of the calculus you use to do the free structure? My question is that when we do free completion in category theory, mostly we are looking for mathematical structures more
oh,
than
wait,
like
Maria,
syntactic ones.
but you are doing a much more free completion is a
I don't
much
know.
more complex than my stupid free category here. I mean, here I'm basically telling you, I start with
Yeah,
a
yeah, yeah.
signature and
Yeah,
I
yeah,
build all
that's
the
why.
terms.
Yes, yes, yes. But usually, as a mathematician, we are interested in nice presentations of such free categories with some properties and which you call completion. So I was wondering whether computer scientists are not interested in this presentation or could have an application to this. On the contrary, what is the free structure you want to get? What are the necessary properties to be applied in computer science? That's what is a more general question. Sorry.
Well, no. From my point of view, the free construction simply means to build terms out of a signature. I can put some axiom just to say if what happens if I have f of AA is the same as having something like let x equal a in fxx or something like that. So I'm just building terms. No higher order, nothing like that. I'm just building terms so that to say I'm just building programs out of a set of methods. The fact is that depending on the very silly axiom that you can put there, well, they are able to represent, I mean, how can I say, I'm thinking about state monad, for example, Haskell. I mean, this is just telling you that if you start with a program and then you equip it with a state monad, well, pay attention because the result is not just a symmetric monadal category, it's a bit more. It is actually
Yeah,
just
you need the completeness. Yeah. Yes. Okay. So you are not. I wanted to know about this free structure. There is a clash between. There is a common behavior between mathematician and computer scientist, or if you have different purposes. That's what my question was behind.
I do not know. For me, I mean, what is the free Cartesian category out of a signature? How would you build it?
Yes, you're not interested in finding another. Yes. No, I understand, but you are not interested in finding a more algebraic presentation independent from the DAC generated structures. That's what I meant.
Well, in general, yes, but if I am then trying to find a normal form for, I mean, a canonical form for the arrows of the free category, of the free Cartesian or gs-monoidal of Markov, then I have to give an inductive generation of the arrows.
Yes, you are interested in the syntactic presentation of it, not in a more
Absolutely.
general, that's what I meant. If you have
Then
a more algebraic, then you could have some completeness, something like that. But this
exactly.
is what yeah, that's what I meant. You could find models and so on. So that's why I was asking you why are you happy when you have
I'm not.
finished?
Let's say I'm not against in principle, but for the graphical presentation, the very, very silly inductive definition of the free construction is necessary. And in the end, for me, it's that one is in the end more important than the models, because I want to have the visual formalism in order to manipulate systems.
Yes, of course. Thank you very much. This was the question, the answer to my question. Thank you.
Thank you, Maria. Thank you, Fabio. Any more questions from the chat? Okay. So let us thank Fabio again, and we're going to end the live stream at this point. Thank you. Thank you, Fabio.
Okay, thanks
Okay,
everybody.
ending the live stream
Here. Okay.
Okay, now we're in the Zoom chat.
Oh, okay.